Hi, hello everyone. I'm Ray Su, co-founder of s3fs. This is actually my very first time speaking at the SDC. And since English is not the language I most use in my daily work and life, so if something I say sounds a bit strange, please know it's just a limitation of my expression. And I'd be happy to continue the conversation with you after talk. Just I mentioned the product I'm working on, it's called s3fs. It's an open source file system made for the cloud. But don't worry, today's talk is not a product pitch, and instead I'll share some story behind why we starting build this product, and some feedback we got from developers along the way. So the title of my talk is why s3fs fail in AI and machine learning workloads, and how to achieve scalable POSIX access. So who has ever tried s3fs before? Yeah, yes. So s3fs is was kind of where we first hit pinpoints, and POSIX is the pathway has kept following in the cloud. Yeah, here is how I structure my talk. Comes in four parts. And first, I'll share what we've learned about the challenge of using s3fs, and then we'll look at why this problem happened by comparing using s3fs with a true file system, and also thinking about the cloud environment and the infrastructure we are working with. From there, I introduced the solution we come up with, which is s3fs, and walk you through some of code design ideas and the principle behind it. And finally, I'll close with two real user stories. So you can see how these ideas work in practice. Back in 2006, when AWS launched S3, object storage started to become really popular, and today it's an essential piece of cloud infrastructure, and the S3 API has basically become one of the de facto standard in the storage world. As you can see on this slide, the core design goals of S3 was scalability, reliability, and low cost. To achieve these goals, they made a key decision: drop the support of full POSIX compatibility. They allow them to keep the system simple and extremely scalable. But here is the challenge. Before S3 came out, POSIX has already been around for 20 years, and thousands of applications was built on top of a POSIX file interface. So naturally, people want a way to keep use the existing tools. And they also want to code with S3. So why the open source project s3fs was created. With it, you can mount it on your system and access it like your local directories. But s3fs, what s3fs does is translate between S3 API and the POSIX API. But this translation comes at a cost. In real workload, the way s3fs behave are very different from what people expect from a true file system. It can cause compatibility issue, performance issue, and stability issue, and even unexpected cost. So in the next part, I'd like to talk about how this issue show up specifically in AI workloads, because AI is a very topic today. And as I know, some AI application developers and machine learning engineers do know the details at the storage layer. Hopefully, what I share here will give you a better picture. So later in my talk, I'll show how we managed to fix this issue while still building on S3. Beyond performance, why do we care so much about being POSIX compatible? Because data pipeline in real world are very messy. Like the pipeline in this slide, maybe you 1 minute working a bash script, and the next minute you need to feed in Spark, then FFmpeg, and then PyTorch. So what do all those two share? They expect a POSIX file system because all of them speak files. So POSIX API, the least friction interface. Object store are very great for static blobs. On your s3fs mount point, try to run ls-l on a directory with 10 million objects, or rename output folder. So you can wait seconds, even minutes. Those list and rename latencies may break down your workload. Now let's take a look at the difference between S3 API and the true file system. The first issue is S3 doesn't actually have real directories. And because of that, rename is not atomic. What happens instead is the object gets copied to a new name, and then the old one is deleted. If you rename a directory, well, since there are no true directory, so what you are really doing is copy every object with that prefix to a new prefix, and then delete all the ones. So you can imagine how much slower it is compared to simply change a directory name in a file system. And the whole process is not in a transaction. And the problem that frameworks like Spark or TensorFlow or PyTorch use directory renames all the time. So this becomes very, very painful. So in fact, engineering team at Pinterest shared exactly this pain at the Spark Summit 2020. You can find the video on YouTube. Second issue is objects doesn't support in-place append or random write. So if you want to modify or append to a file, you can't just write to end of the file. You have to download the entire object and modify locally and upload to the whole things back to S3. So that makes many data process program basically unusable on top of plain S3. So on the third problem is there's no global locking and no some POSIX features like hard links, extend attributes, and permission control don't really work well across multiple nodes. And another big problem is metadata operation. Since like list and states sound simple, but on S3 very expensive. If you have millions of small files, just listing them can take a huge of time. Small and random I/O is also painful. Each time you call S3 API, the latency can actually be longer than the time it takes to read the data itself. So in the end, the performance looks pretty bad. And there is an issue of bursty workloads. Imagine the start training job when hundreds of workers suddenly started listing and opening file. That's often trigger S3's 503 slowdown errors. To survive that, you need to exponential backoff, retry, and request shaping. But most of the team don't build that in their code. And finally, S3 gave you a strong consistency, which is great, but don't confuse that with true file systems transactions. It doesn't magically give you atomic rename or transactional guarantee. So even with strong consistency, it's still not the same with a true POSIX file system. On S3, small files are not just slow, they are very expensive. Every request costs money, and even in intelligence tiering, anything under 128 kilobytes is always built at higher rate. So if you have a million of tiny files, your build will explode. But to fix this is simple. Pack them up. You can use formats like ZAP, tar, WebDesite, Parquet, Lens, TF record, and FF record. Yeah, it's rely on your workload. So let's take a look. What's this look like in a real training job? And the classic way of writing a checkpoint is write to a tempo file, flash it with fsync, and then do an atomic rename. That's safe pattern every deep learning framework will rely on. But on s3fs, the pattern simply doesn't hold because rename is not atomic. We see the same issue in Spark job as well. Another common pain, when you start an epoch, all those state loader processes wake up at the same time. They start calling S3 with tons of list, head, and small get requests. The result is a burst of metadata traffic. And your training job slowed down right from the start. And one more thing is there's no true append in S3. So every time you try to append or modify your file, what really happens is a full rewrite of the object. So unless you move to special bucket type, which are not general S3 everyone is using. So here is the bottom line. If your workload needs atomic rename, proper locking, lots of concurrent writes, or really fast metadata operation, and you need all of that to run reliability at scale, the s3fs is not the right tool. But remember the pipeline we looked at earlier. Many of tools in the pipeline still depend heavily on full POSIX compatibility. So as that means, in many cases, have a truly POSIX-compliant file system is still the easiest and the most practical choice for AI and machine learning workloads. In practice, here's a reality. When it comes to semantics, POSIX give you the richest support, and then HDFS, and then S3. That's why POSIX is often the easiest fit to messy and real-world pipelines. So when we look around at the distributed file system, none of the classic ones were really designed for the cloud, include s3fs, Lustre, BDFS, GlusterFS, and even HDFS. So all of them come from a pre-cloud year. AWS released his first managed elastic file system in 2016. It's a full 10 years after S3. And the price, roughly 10 times the price of S3. So for today's AI workload, with data size exploding, that's a deal breaker for many users. So what do people do? They end up putting all their data in S3, and they need to manually copy the how data they need into EFS. And once they done the job, they have to delete it and copy the result back to S3. And if the old data in S3 changes, they have to synchronize it again. So you see the problem. To manage consistency between two systems, S3 and the EFS, is become a constant headache. So and even you try to save money with EFS infrequent access, that is not a solution at a terabyte scale, because the storage price is close to S3. But every time you touch the code data, you need to pay an extra fee to extra retrieval fee. So if it's about $10 per terabyte. So if you do a full scan or a shuffle across hundreds of terabytes, quick add up to you a huge bill. So when we look at the design of a distributed file system like HDFS, s3fs, or Lustre, even going back to original Google file system paper, or we can say a common pattern. All of them have two major parts: metadata management and data management. And data management layer is responsible for how actual data block are stored across a cluster of disks, placement, replication, and disaster recovery. If you think about it, it's not so different from what S3 does. So in many ways, we can imagine S3 as an elastic block device, and it's durable. And if you put your own partition table on top of it, it already looks like the beginning of a file system. So when we start design s3fs back in 2017, we set 3 clear goals. First, keep metadata completely separate from data. That way, each part can scale or fail over on its own. If you need more directory lookups, to only add more metadata nodes. If you need more throughput, just add bandwidth on object storage. So the two doesn't compete with each other. And second, store actual file blocks on object storage, because it's a cost efficiency, it's scalable, it's durable by design. And then by use local disk on computer nodes as cache, you can boost the performance significantly for hot data. And third, stay in user space with fields. Just give us one single binary, then mount on any Linux kernel in container, even some serverless environments. So no kernel patches. On the right side of this slide, you can see the architecture of s3fs. In the beginning, we actually package as a full managed cloud service and shipping on every public cloud. So besides the metadata and the data management layer, we just talked about, there is another very important piece is caching. So in our first design, the cache was mostly for read. And why is this important? In AI and data analytic workloads, read performance made a huge difference. So by keeping hot data in the cache, we can deliver much faster rate, and at the same time, caching is also cuts down the number of API calls. So fewer S3 API call means lower latency and lower cost. Yeah, this slide shows a very simple benchmark where we compare with s3fs, EFS, and juicefs. Yeah, we only test the sequential read and write, but you can already say juicefs demonstrates strong concurrency. As throughput scales up as you add more processes and or more clients. So the chart shows is a single client running multiple processes. And then multiple clients as well. Yeah, and as you add more processes or more clients, bandwidth keeps growing in very predictable way. On the right, you can see an overview of most recent MLPerf benchmark results. What is exciting is that juicefs performed really well in Ethernet-based test, showing strong scalability and throughput, even without specialized interconnect. So I won't dive deep into performance today. It's a very rich topic. So if you are interested, so you can catch me later and we can chat more. Yeah. And in 2021, we upgrade architecture again and released the open source version of juicefs. And when we launched the community edition, we made a clear promise. It has to be simple and cost efficient. So just one command to deploy and almost no babysitting, and the cost model was basically S3 plus a small metadata store. So that's good enough for most workloads. We also keep it open by design. Developers can welcome to extend it and swap up some components and even rethink the parts of the stack. It's not just a working file system. It's also a living blueprint people can build on. In the very first release, the version 0.1, metadata was supported only on Redis. And just 12 months later, when we ship our first GA version, metadata become fully pluggable. It has already supported Redis, MySQL, PostgreSQL, Tightheavy Foundation DB, and even SQLite, Badger DB, etcd, whatever you name it. And everyone has their own advantage and disadvantage. So you can choose by yourself, rely on your workload and experience. Here is the first real story from MapWorks. It's a company built software for biology informatics workloads. And what you are seeing is a RNA sequencing pipeline, and they run in the cloud. To keep costs down, they use easy to export instance for compute and S3 for storage, and mount it into cluster with s3fs. But at first, made a lot of failed tasks. After digging, the root cause was clear. The workloads was generating huge number of tiny files, many less than 1 kilobyte. So each small write through s3fs was painfully slow and many simply timeout. So and after switching from s3fs to s3fs, you see the field task gone, and when you compare the total runtime of pipeline, we notice a clear improvement. With s3fs, the job took 26 hours, and with s3fs, it's finished in just 7 hours. About the same runtime you get with AWS EFS. Yeah, and second user story comes from Latent AI. They provide multiple cloud, multiple region GPU management for their customer, and it's been so exciting.
This one right here. Take this off. Couldn't take it off. I'm just going to attach this right.
Oh, okay. Voice is clear? Yes. Oh, yeah, go on. Yeah, in Latent AI's architecture, they first use AWS EFS to store data and to support customers' data cleaning and training. But the storage was expensive. And whenever data had to move across region, so transfer cost was also pretty high. So later they switched to EFS with Cloudflare R2 because R2 has no egress fee as the storage backend, and that's cut their overall cost by 98%. All right, let's wrap up with 3 takeaways. First, S3 is amazing. They give us unmatched scale, durability, and cost efficiency. And s3fs makes it really easy to mount. But once you get into a mixed read and write workloads and a large directory listing or heavy concurrency, I think s3fs is not the right tool. And second, build on top of S3 doesn't mean you have to give up the POSIX interface. With the right design, you can create a file system, field nature to applications, and still cloud native. And third, this is not just a theory. s3fs is already well used in AI, from training pipeline to large-scale inference. So it's helping teams get rid of our bottleneck every day. Yeah. So that's all. If any of this sounds interesting, I'd love to keep a conversation. Yeah, welcome to join our Slack channel or follow us on LinkedIn and X for updates. Thank you so much for your time.
That data is immediately visible in the file on the other
Oh yeah, yeah. So I will change the we need to submit to the metadata first, and so when change submit into metadata, other clients can see the change, and by default we don't enable metadata cache. Yeah, and if you very clear about your workloads, you can enable metadata cache under a TTL in prior policy.
What about the data? When one client has written the data, how quickly it becomes visible on a different client? Do you like immediately push to the object storage and the other client needs to know that whatever that client cached earlier is already stale and it needs to read again from the object storage?
Yeah, so our client with data, they need to visit metadata first. So the metadata engine is the centralized engine. Yeah, I'm not sure I answer your question.
I mean, do you mean that on every single read, the client has to consult with the metadata service?
Yeah. Yes.
On every single read?
Yeah.
Wow.
Yeah.
Thank you.
Just to clarify, you're saying that in a system that needs strong consistency and high concurrency, you're turning off your cache.
Yeah.
Is that what you're saying? So you turn off the metadata cache.
Yeah, but in community edition, there's no metadata cache by default, but you can configure a data cache on your computer nodes. Yeah.
The data cache is relatively harmless, though, but the metadata cache is not there.
Pardon?
You're saying the metadata cache is disabled on the communication.
Yeah, yeah.
Eventually, when you have to read, you can end up having a lot of overlapping slices.
Sorry, I don't fully understand.
So when you have small writes, you end up writing it in terms of slices, right?
Yeah, yes, yes. We store actual data block in S3. We chunk the file by default 4 megabytes as a block stored in the object store. So if you random write or change some of file, we will create a slice and write to S3 and update the metadata, and we never change the block already in the S3.
So your read has to do consolidation of these slices, right?
Sorry.
So your read has to be aware of all these slices which
Yeah.
can happen, which can overlap with
Yes.
each other in a single block.
Yeah.
So your read would be slow because of that, right? So how do you handle that?
Yeah. When we read, we need to yeah, how to express? We need to scan the metadata and compact the metadata index. So if you have a lot of changes, a lot of writes to a file, they will async to compact the data in the object store. All right, that's all. Thank you.